Good evening to all of you. How are you guys? Good evening to all of you. Today we are around half an hour late, so sorry for the inconvenience. So let me tell that whether my voice and video is clear to all of you. Audio and video is clear to all of you. First of all, I want from you guys, audio and video is clear to all of you. It's clear. Vacunt is telling say it's clear. Okay, so if audio and video is clear, so let's start the class for today. In my yesterday class, I have discussed regarding definitions as well as the difference between the OCF and the pipe flow part. So in today's class, we are going to start the new topic or new point, that is a classification of open channel flow. So classification of open channel flow we have done on different basis. One of the basis is that based on the thing whether your parameter, flow parameter like depth, then velocity, then discharge, if these are changing with the time, then we call it say unsteady flow. If it is not changing with the time, then we call it say steady flow. So steady flow occur when the flow properties such as depth or discharge at a particular section do not change with the time. If the flow properties such as depth and the velocity at a section changes with the time, then it is known as unsteady flow. So if you want to write this thing in a mathematical way, for a steady flow, dover q upon dover t will be 0. Dover y upon dover t will be 0. Even differentiation of v divided by, like with respect to t, will be 0. So flow parameters are not changing with respect to time at any particular section. This point you need to remember, at any particular section. Similarly, if they are changing, in that case it is an unsteady flow. Okay, so I hope you have understood about steady and unsteady flow in open channel flow. Next one is uniform and non-uniform flow. So last time we had comparison for, like, we want to find out whether our flow parameter are changing with respect to time or not. This time we want to find out whether our flow parameter are changing with respect to section or not at any particular time. That means if the velocity of flow is constant at all section at a given time, it is called a uniform flow. So here they have mentioned only velocity, but that doesn't mean that always velocity you need to take. Even depth also will be included, even discharge will be also included. So if flow parameter is constant at all section at a given time, it is called as uniform section. And practically, if the depth of flow is constant at all section at a given, for example, if q is constant, if depth is constant, so velocity will be constant, na? So that is the reason they are telling, like, practically if the depth of the flow is constant at a section at a given time, it is nothing but a uniform flow. And if it is not constant, in that case it is a non-uniform flow. So for example, let us say this is the section. and your depth of flow is like this. Your depth of flow is like this. It is changing. With respect to section, it is changing. So it will be a non-uniform flow. It will be a non-uniform flow. I hope you got this point. I hope you got this point. So uniform flow and non-uniform flow. Practically, if you want to see, basically you can see when the depth is constant throughout the length, we call it a uniform flow. If it is not constant along the length, we call it a non-uniform flow. So this point should be very clear in your mind. Is it noted? Tell me whether you all guys are noting down all these things parallelly with me. Okay. Now see the characteristics of uniform flow. So in a uniform flow, definitely there will be some characteristics which you all can see. For example, let us try to understand. Let us try to understand. This is the datum. This is the channel bottom. This is the water surface line. And this is the TEL line. So let us give the name for everything. This is channel bottom. This is HGL line. And this is TEL line. Here I am introducing 3 slopes to you. That slope name you need to always remember. First one is S0. Second one is SW. And third one is SF. S0 is slope of channel bottom. Slope of channel bottom with respect to horizontal. With respect to horizontal. Always remember, here the slope of this channel bottom with respect to horizontal will give you nothing but S0. Second is the SW. Slope of water surface with respect to horizontal. And the SF is the energy line slope with respect to horizontal. So this line slope is S0, this line slope is SW, and this line slope is SF. And all these slope we are taking from, or we are taking a reference as horizontal. So horizontal, actually we are horizontal direction we are using. So basically S naught, if you see, this is the S naught, this is the SW, and this is the SF. Okay. Now what I'm telling here, what characteristics of uniform flow I'm telling, in a uniform flow, understand, as you said, depth is constant throughout the flow. So if depth is constant throughout the flow, these line and this line will be parallel. That means channel bottom and this HGL will be parallel. And if channel bottom and HGL is parallel, in that case S naught will be equal to SW. Can I say like this? S naught will be equal to SW. I don't think so anybody will have any problem. Now, as you only told that in a uniform flow, even velocity is also constant along the section. Velocity is also constant along the section for a uniform flow condition. So if velocity is constant, you know that difference between TEL and HGL. What is the thing which actually separates TEL line and HGL line? It is nothing but the velocity head. It is nothing but the velocity head. And if velocity is also constant, that is a case for a uniform flow. So if velocity is also constant, that means what? That means this velocity head is also constant. So again, this HGL line and TEL line is again parallel. So if HGL line and TL line is again parallel, so can I say this? This SW is also equal to SF, and this become characteristics for the uniform flow, that in a uniform flow, your water surface slope, your channel bottom slope, your energy line slope, all will be equal. And that becomes condition for the uniform flow. That becomes condition for the uniform flow. That becomes condition for the uniform flow. Is it clear, my dear? Is it clear, my dear? This is something we call as characteristics of uniform flow. Now in this characteristics part, if you have noted down these part, then I can go to the next part. This part, have you noted, all of you? This part, have you noted? Please reply me in comment, na? Whether you guys have noted or not. Otherwise, I will not give time for noting down things. Right now, I'm asking for whether you have noted or not. That means I'm giving you time to note down each and everything. Okay. So if you have noted down these things, then I'm going to the part that's something we are calling as conditions for the uniform flow. So just now we have understood about characteristics of uniform flow. Now we are going for the condition for the uniform flow. Okay. So look at the thing first. This is the channel datum line. This is the channel bottom. This is the water surface line. So a particular stretch of the river I am taking, a particular stretch of any flow I am taking. For example, L length I am taking. Okay, this length I am talking about. So in this length, you will have a weight. you will have a weight of this water or weight of this liquid mass. That is nothing but the W. That is nothing but the W. That weight, I am taking two component of that weight. I am taking two component. One is along the length of flow and next one is perpendicular to the length of flow. So this we are naming it as FD. If this is W, this is theta, this is theta. So definitely if this is theta, so any line which makes perpendicular will make this also theta. So this becomes W sine theta, if I am not wrong. This becomes W sine theta, if anybody will having any problem. Why this name we have given FD? D indicates driving force. So if water is flowing in this downward direction, because of this W sine theta force only, because of its weight only, the water is flowing down, na? So in that case, which force is actually pulling that water down? It is nothing but the W sine theta. It is nothing but the W sine theta. I hope it is clear to you. Now, if any force, any driving force pulling this water down, definitely there will be a resistance. And that resistance will be here. That we are naming it as FR. Now try to understand the condition of uniform flow. If your driving force is more than the resistive force, which happens generally in a steep slope, your driving force is more than the resistive force. In that case, that flow cannot be a uniform flow. That flow will be always uniform flow when condition, look at here, when your FR is equal to FT. When your resistive force and driving force are same. Resistive force and driving force are same. In that case only it is possible that uniform flow will occur, because see, driving force will be more than the resistive force. In that case it will not be a uniform flow. What will happen in that case? Your depth will be changing in that case, like waterfall. So in that waterfall, your FD is more compared to FR. So there will not be a case of uniform flow. That will be a non-uniform flow. Now if you write this part, you can write like this. Resistive force will be shear stress into area. A driving force will be W sine theta. Okay. Now if you want, you can find out the formula of tau also from here, like tau into area. So for example, if you see the tau area here area will be nothing but equal to what? Or here even W will be equal to what? W we can write as gamma into volume. That volume we can write area of cross section, so AC into the length into sine theta. And here area will be, see, if you see this area na, look at here. This is the section. This is the cross section area. This is the cross section area. This is the length. This is the length which I am showing to you. This is the length. This is the cross section area which I am talking about. So area, cross section area, AC into length will give you the volume. And you know that weight is nothing but a specific weight into volume. So that is the reason I have written a specific weight, that is gamma into AC into L. Now, if you see perimeter is what? This length plus this length plus this length will give you the perimeter of this cross section. And if you multiply that perimeter into this length, it will give you the surface area. Surface area means what? This area, and this area. These are the areas from where you are getting that resistive force. We are getting that resistance. So in that case, here I am writing P into length, perimeter into length. So tau will be L and L will get cancelled out. Gamma AC by P into sine theta. So tau will be equal to gamma A by P, you know it is R, hydraulic radius, and sine theta you can write as S naught. So here sine theta you can write, if theta is small, sine theta will be equal to tan theta will be equal to theta itself, and R is nothing but we call as hydraulic radius. This you will learn in the next topic, hydraulic radius, which is equal to area by perimeter, weighted area by weighted perimeter. So this part have you understood? So this becomes condition for the uniform flow. This is nothing but a condition for the uniform flow, that your FR should be equal to FD. Your FR should be equal to FD. Okay. So is this clear to all of you? Tau equal to gamma R S naught. Tau equal to gamma R S naught. Is it noted? Okay. Coming to the next part. Now the second one is the non-uniform flow. So in a non-uniform flow, we have different types of non-uniform flow. First we call as GVF. Second we call as RVF. And third we call as SVF. What is the meaning of these? Gradually varied flow. Gradually varied flow. This one is rapidly varied flow. And this one is spatially varied flow. For GVF, gradually varied flow, again we have two type. One is steady, another is unsteady. Steady, unsteady. Steady, unsteady. So total in non-uniform flow, total 6 type we have. GVF steady, GVF unsteady, RVF steady, RVF unsteady, SVF steady, SVF unsteady. So that you need to understand it. Okay. So first we are seeing the gradually varied flow. So what they are telling, name itself tells you gradually varied flow. That means changes or changes will be there. Here we are talking about change in depth. So change in depth will be there, but that change will be gradual. If the change of depth in a varied flow is gradual, so that the curvature of streamline is not excessive, such a flow is said to be gradually varied flow. In other words, if a small change of depth occur in a long span of time or distance, we call it a gradually varied flow. For example, if you want to see, I'm giving an example for a steady GVF. So this is a dam we have. This is a dam we have. So in the back side of the dam, or you can say the upstream of the dam, you will find the water is going like this, or in a little bit more clear way, it is going like this. So if you notice, my dear, there is small change in depth which happened here. There's small change in depth. So in a long span of distance L, small change in depth occurs. So this type of change we call it as non-uniform flow. So it's example of steady GVF. Why we are giving it as steady GVF? Because with respect to time, this change is constant. Like right now, whatever change you are finding out, different time you will come, again you will find the same change. So that's something we are calling it as steady GVF. But now assume for unsteady GVF, example I'm giving to you, I think you all can understand completely. Flood wave, flood wave during a flood wave in a river. During flood, whatever the waves comes in our river, that waves will be having, like they all are non-uniform flow waves, but at the same time that waves are not constant. The wave dimensions or the wave depth are not constant with respect to time. Certain wave will have different you will say different change in depth, another wave will have different change in length. So in that case, that flood wave is nothing but a perfect example of unsteady GVF. In flood wave, depth are not so high in a river, if particularly about river case, but it is unsteady. It is unsteady. So that is the thing which you need to understand. So for both, I have given you example. One is the flow of water in the upstream of a dam, and second one is the flood wave in a river. So this point you need to understand. This is something for the gradually varied flow. Anyway, I will be discussing gradually varied flow in a detail because it's a separate topic for you. But here a small introduction I am giving regarding the GVF. What is the meaning of GVF that I have given to you? Second one is the rapidly varied flow. Now second one is the rapidly varied flow. So what is the meaning of rapidly varied flow? If large change in water level occur in a short distance, very large change in depth occur for a small length of section, we call it say rapidly varied flow. Example is nothing but the, again for study and unstudy example will be different. Study RVF example will be hydraulic jump, and for unstudy RVF example will be surge wave, even tidal waves which you see in your ocean and all. So these are nothing but the unstudy RVF. Hydraulic jump and surge both are a separate topic. There I will discuss in detail. Right now just note it down the examples. Now the third comes, that is a spatially varied flow. So here what is actually happening now? See, for example, if you are adding some flow to the river, or for example, if you are like this, there is a flow which is going on and you have added another flow in that. So definitely what will happen because of this, there will be change in water level because you are adding something. Similarly, if you are removing something, if you are abstracting something, again there is a change in level of water. So that's something we are calling it as spatially varied flow. If flow rate is either added or abstracted from the flow system, it is called as spatially varied flow. So that is the meaning of the spatially varied flow. Here also we have steady SVF and unsteady SVF. Here also we have steady SVF and unsteady SVF. For steady SVF, generally steady SVF will come when a particular section is added. So you can write like flow is added at a uniform rate through wear. And unsteady SVF will come during rainy season. During rainy season, what happens? From all the directions, waters are coming now. Because of the surface runoff, from all the direction in a river, water is coming, and in that case, your change in depth will not be uniform. Your change in depth will not be constant with respect to time. It will be non-uniform, but it will not be constant with respect to time. So that I am telling. Surface runoff during rainy season. So that I'm giving a hint to you that surface runoff during rainy season I hope you have noted down this part. I hope you guys have noted down this part. Till here it is clear to everyone? Till here, is it clear to everyone? Till here, is it clear to everyone? Till here, is it clear to everyone? Okay. So now a new topic, that's something we are calling it as channel geometry, and it's a very basic topic in your OCF. So I want all of you to understand it very clearly. So here few things I will be teaching you how to calculate it. These are new for you, I know, but very soon you will be very comfortable with these things because these are the basics of your open channel flow. And with this, without this, you will not be able to solve any numerical. So I want you all to focus here. I want all of you to solve these things with me. So in a channel geometry, what we are doing here, let us take a typical setup. So this is a trapezoidal section basically. So this section is having width, we are representing as y. This we are representing as b. So this is the depth and this is the width. Okay. Few things which you need to understand. A is the weighted area here. P means weighted perimeter. See, weighted area means those area which is actually in contact of water. Area which is not in contact of water, that area of cross section we are not taking. For example, in a rectangular cross section of flow, area will be b into h. But what we have found, the actual depth of flow is not up to h, not the full depth is happening, only the half flow depth is happening. So in that case, our weighted area will become b into h by 2. I hope you got this point. I hope you got this point. So this will be the weighted area and the weighted perimeter. Next thing which you need to understand is the width. So that is nothing but the b. But T here is nothing but we call as top width. T here is nothing but we call as top width. T here is nothing but we call as top width. So if you want, here you can write down, T in place of P. So T means top width. Next thing, R, hydraulic radius. Hydraulic radius. We call it as A by P. So R is hydraulic radius, that is area by perimeter. Next is the D, hydraulic depth, area by top width. Hydraulic depth, area by top width. So D is equal to hydraulic depth. D is equal to hydraulic depth. So what I will be doing here, I will be giving different section to you, whether it's a rectangular, triangular, trapezoidal, circular, these type of section I will be giving to you. You need to tell me the R value and D value. R, D and T. These three value I will be expecting from all of you. So let us start with the first one. First is nothing but the rectangular section. So first one I will be teaching you rectangular section. Rectangular section. A rectangular channel. So this is the channel. This is the channel. This is the channel. This is the depth. This is nothing but the width, B, which is given to you. So as I said, three things I'm interested. First one is the top width will be nothing but equal to B. Top width is nothing but equal to B. Area will be B into Y. And perimeter will be B plus 2Y. Now, two things I need to find out. First one is the R. area by perimeter. So it will be by upon b plus 2y. And d will be area by top width. So it will be by divided by b. So d will be equal to y. So always remember, in a rectangular section, the hydraulic mean depth or hydraulic depth is something what we call as y. Something which we call as y. Is it clear to you? Is it clear to all of you? Now here, for this case, I'm writing a special case for all of you. Special case, if B is very much greater than Y, when it will happen? For example, Ganga river is flowing in a planar area. There you will find the depth of the Ganga is very much lesser compared to the width, or width is very much higher compared to the depth. So this is the condition, B is very much greater than Y. This is something we are naming it as wide rectangular section. Wide rectangular section. Wide rectangular channel. So in that case, R will be equal to what? See, B is very much greater than Y. So this 2Y I can neglect it. Na? So it will only become R equal to Y. R equal to Y. But this case is only possible when it is given in the question it's a wide rectangular channel. If it is not a wide rectangular channel, we cannot use this special case. We cannot use this as a special case. I hope it is clear to all of you. Kindly note it down. And if noting down is completed, you can try for the triangular section. Okay. Now we are going for the second one, is the triangular section. Triangular channel. So triangular channel is like this. Triangular channel is like this. This is the depth. This angle we take it as theta. Okay. Slope what we are having is 1:m. Slope is 1:m. First thing T. If this is 1, this is M. 1 vertical, M horizontal. So if this is Y, this will be My. Here also my. So top width will be 2 my. Top width will be 2 my. Area will be half into base 2 my into y. So it is my square. Perimeter is nothing but 2y root under 1 plus m square. Perimeter is nothing but 2y root under 1 plus m square. That is the perimeter part. That is the perimeter part. That is the perimeter part. So P is equal to 2y root under 1 plus m square in the perimeter part. In the perimeter part. So area we got, perimeter we got. Now we can easily find out R. So first find out D here. That is area by top width. So area will be my square divided by 2my. So it is y by 2. So here for the rectangular section, D is equal to y by 2. This part you need to remember. This part you need to remember. Next thing is the R. Next thing is the R. Area by perimeter. So area we have again my square divided by perimeter 2y root under 1 plus m square. So here again a special case will come. So special case. In special case what we are taking? We are taking theta as 45 degree. So if theta is 45 degree, tan theta, tan 45 will be equal to 1. So in that case, m will be equal to 1. If m is equal to 1, r will become what? It will be y by 2 root 2. Y by 2 root 2. So this you need to remember. When theta is 45 in a triangular section, your r will be equal to y upon 2 root 2. So this is the special case which you need to remember. Okay. Now the third case is trapezoidal section. Trapezoidal section. Now the third case is trapezoidal section. So it will be like this. It's a combination of rectangle as well as triangle. So this is the depth. Here the outside angle they have taken as theta. So remember here, slope will be again 1:m only. This is nothing but B only. So if somebody will ask you top width, it will be B plus 2my. Area will be by plus my square. Perimeter will be b plus 2y root under 1 plus m square. So R value will be area by perimeter. So by plus my square divided by b plus 2y root under 1 plus m square. This is the formula for R. And for D we have area by top width. So for that we have formula by plus my square divided by top width, we have b plus 2my. So that is the D part. That is the D part. I hope you got this point. I hope you all guys have understood about the trapezoidal section. Now the next one is the fourth one is the circular section. Circular section. So it will be like this. It will be like this. So up to here the flow is occurring. This is the center. This is the center line. Center line radius is R. Here the radius is R. This angle they have taken as theta. This angle they have taken as theta. So first thing first, top width. Top width, that means this distance from this to this, A to B. So R cos theta and R sin theta. So R sin theta plus R sin theta, that means 2R sin theta will be the top width. Second thing, to find out area. See, area directly, this area you cannot find out. This area we need to find out now. So this area you cannot find out. So what you can do here, you can find out this sector area minus this triangle area. So sector OAB area minus this triangle OAB. That will give you the area for the hatch part. Area for the hatch part. So what we can do here, for sector area, it will be nothing but pi r square divided by, one second. Let us write 2r sin theta. So let us give this name as, this is r, small r, not capital R. Otherwise you will get confused between radius and hydraulic radius. So that is the reason I am writing as 2r sin theta, small r sin theta. Area will be nothing but equal to what? Pi r square divided by 2 pi into 2 theta. This will give you the sector area. Minus half into base into height. So 2r sin theta into r cos theta. So area will become r square we are taking at common. So r square by 2 we are taking at common. So r square by, this will be 2 theta minus sine 2 theta. This becomes formula for area. Similarly for perimeter. For perimeter, what we need to do, see, if this 2 theta is 2 pi, so in that case perimeter will be 2 pi r divided by 2 pi into 2 theta. So this will become 2 theta r. So we got a formula for A, we got the value for perimeter. Now it's easy to find out R as well as D. So R will be equal to nothing but equal to R squared by 2 bracket we have 2 theta minus sine 2 theta divided by area by perimeter. So divided by 2 theta R. So what we got? R upon 4 theta. In bracket we have 2 theta minus sine 2 theta. This is the formula for R we got. This is the formula for R we got. R by 4 theta, 2 theta minus sine 2 theta. Similarly for D, what we will get here? In similarly for D, D will be A by T, na? A by T. So we are getting it as R by 4 sine theta, R by 4 sine theta. For D we are getting as R by 4 sine theta, 2 theta minus sine 2 theta. R by 4 sine theta, 2 theta minus sine 2 theta. R by 4 sine theta, 2 theta minus sine 2 theta. I hope it is clear to you. I hope it is clear to all of you. So generally what happens? Two cases are possible. In a circular channel, either half flow or full flow will occur. So in a half flow, theta will be equal to what? It will be equal to pi by 2. In half flow, this theta will be equal to pi by 2. So if you put pi by 2 in R you will get around d by 4. D is nothing but the diameter. R is nothing but d by 4 you will get. You can put it, this theta you need to put it in this formula. Then you are getting R as d by 4. D by 4. And what about D? That you are getting as pi R by 4. Pi R by 4. If you put theta equal to pi by 2 in D formula, you are getting D as pi R by 4. This is for the half flow condition. For full flow condition, where theta is equal to pi by 2, R is equal to, in that case, R will be again equal to, for full flow condition, theta will be pi, not pi by 2. R will be equal to again d by 4 only. Same you are getting as half flow. And d will be infinity. Because you know that when the full flow is occurring, it is not an OCF. Not in case of OCF. Not in case of OCF. This point you need to always remember. It is not a case of OCF. It is not in case of OCF. This point you need to remember. It is not in case of OCF. It is not in case of OCF. So generally one questions comes that question I will discuss tomorrow. When I will be discussing Manning's equation, then this question I will ask you. Till now it is clear to all of you? Okay. So today we have completed our two topic. One is the classification of open channel flow and the second is the channel geometry. This channel geometry is very, very important for all of you. I want all of you to just revise because these are the basics for the numerical calculation. Like in question, if somebody will give you, it's a wide rectangular channel. wide rectangular channel, that means in back of the mind you need to understand here r will be equal to y. So these point need to remember if you want to solve question for gate or ESE. These small point you have to always remember. Okay, so today class will discuss up to this only. From tomorrow I will be starting a new topic that you can no, tomorrow again I will be discussing some introduction part only. So tomorrow I will be discussing Froude number, Reynolds number, velocity formula, Manning's equation, Chase's equation, then Stiegler equation. So all these small basics of the OCF that I will be discussing. Most probably tomorrow or day after tomorrow yours introduction part will be over, and after that I will starting a new, or I will starting the first important topic for OCF, that will be hydraulic efficient section. But all these basics which I am telling to you now, these basics are very much required to understand that main concept, otherwise you will not understand OCF completely. Okay, so tomorrow again topics will be introduction only, in introduction only. Topic name already I had told you. So tomorrow again I will be meeting at 8 p.m. Today because of some inconvenience, class got started at 8:30, but tomorrow it will start at 8 p.m. only. Okay, thank you everyone, good night.